Let's have a closer look at numbers and strings in this module. Now, obviously, we work with both a lot throughout this course, and we'll not start from scratch. Instead, we'll have a tiny look behind the scenes and dive into some advanced features or features we simply haven't really worked with thus far. To be precise in this module, we'll have a look at numbers, how they are actually represented internally, and why we sometimes end up with strange results in certain calculations. We'll have a look at the global number and math objects or constructor functions and what we can do with those. And we'll also dive into strings again, and there also revisit template literals, because it turns out with those we can do more than what we did thus far. Now let's start with numbers. Numbers are, of course, an important construct in JavaScript. And it's important to keep in mind that in JavaScript, every number is a floating point number, which means a number with an integer place and then also with a couple of decimal places. So there is no specific integer type for numbers without decimal places. That does not exist in JavaScript. We do have a special integer type in certain other programming languages, but JavaScript is not one of them. Every number instead is a float, which means a number with decimal places. Now, internally, numbers are stored as 64-bit floating points. So there are 64 bits available to internally represent a number. Bits are these things which can be either 0 or 1. 1 bit is reserved for the sign, so if it's a positive or negative number, and the other bits are basically there to represent the digits of the number and where the dot is, so where the decimal separator sits. And the combination of these bits is therefore capable of describing numbers, of course within certain boundaries. Now, before we have a closer look at these boundaries, if you want to learn all the theory about floating point arithmetic and how numbers are represented as bits, not just in JavaScript, but in any programming language, you can check out some of the attached articles and resources like the Wikipedia article or this discussion on Stack Overflow. There you can dive much deeper into this, something I won't do here simply because it's not really the core of JavaScript. It's definitely interesting to notice and to understand this, but for your day-to-day work, you typically won't need this, which is why I will ignore it here. The important takeaway from these resources, or without them, by just listening to what I'm saying here, I guess, is just that, of course, due to the fact that we have 64 bits available to represent a number, there are certain limits in JavaScript. There is a maximum and a minimum number, and there also is only a certain amount of precision we can get regarding the decimal places of a number. So you can't represent every number in JavaScript. And there are, of course, certain ways around that if you really need to, though, of course, we're talking about very large numbers or numbers with lots of decimal places. And the question is how often you really need to work with such large numbers or with such detailed numbers. But be aware of the fact that there are certain limits. And these limits are actually with what I want to start here. Attached you again find a very basic starting project, HTML file and an empty script. And for now we'll just work in the console here. Now in JavaScript we have a maximum and a minimum number. And you can easily find out what the maximum and the minimum is by using the global number object, which is built into JavaScript. And then with a dot, you got a couple of methods and properties available. And for example, there's a max save integer. And this gives us just what it sounds like. This is the biggest possible number you can represent with the normal number type in JavaScript. That's 9 quadrillion, so a relatively large number. And just in case you're interested, it's basically the same as 2 at the power of 53 minus 1, which you can calculate with the math object where we have a power of function. Basically the same function we wrote in the functions module with our recursion built into JavaScript on the math object. And there you can enter 2 at the power of 53 minus 1. This is the largest number JavaScript can reliably produce. Now you might wonder why we then can also print this this number, the thing simply is, whilst JavaScript can display this number, calculations with such a number will not really work. For example, if we add 1 here to this limit, you see this number was not changed. We get the same result as when we just output the number. So that proves that this is the highest possible number we really can work with. Of course, if we would add anything to that number, we again would enter that range where JavaScript is not able of representing it, and therefore working with that number is only possible if you deduct something from it, basically, or if you divide it by some other number. So that's how you can think about this maximum number. Of course, you don't just have a maximum integer, you also have a min-safe integer, which is essentially the same number with a negative sign in front of it. And you also have a max value here. The difference is that this is actually a decimal number. So here we don't have the largest integer, but the largest number we can express. And in the end, that's 1.79 and so on, multiplied with e at the power of 308. So that's the biggest value you can work with in JavaScript. Not the biggest non-decimal value, so not the biggest integer, but the biggest value in general. And these biggest and smallest values in integers simply result from the fact how JavaScript numbers are represented internally, how they are stored in these 64 bits in the end. Again, the resources attached to the last lecture are a great way of diving deeper into that if you want to learn all the theory behind that. The core takeaway here is that if you ever should work with such detailed or large numbers or integers, you want to be aware of the fact that there are limits. You want to be aware of the fact that, for example, you can't deduct anything from that number because it already is the smallest possible integer. You can't deduct any other integer, I should say. You can't add anything to that number because it already is the biggest number you can represent in JavaScript. Now, if you still do add something to that number, or you do deduct an integer from that number, you don't get an error, as you see if I deduct 10 here. The thing just is, JavaScript gives you an imprecise result. For example, here you see we exceed that bit range, and therefore we simply get the result where JavaScript cuts the number after its 64 bits and then converts this back to a decimal number, so in a decimal system, I mean, with a base of 10, and that would then be this number. So it can be difficult to wrap your head around that because we're also working with two different number systems here. The decimal system with a base of 10 and the binary system with a base of 2, which of course gets used when we work with bits where we only have 0 and 1. That is what the binary system is all about. And therefore, JavaScript internally works with the binary system and then always converts it back to the decimal system when it outputs that number. This is how such a strange result happens when we deduct 10 from this number. We exceed that bit range, which is available for numbers, and then JavaScript just cuts off the bits and converts that bit, that binary number, back to a decimal number, which would be this one. Now, again, can be tricky. You rarely, of course, work with such large numbers or with numbers with that many decimal places here in the end, but it's important to be aware of the limitations you might be facing. Speaking of the binary system and the decimal system, you might remember that sometimes throughout the course you got a strange output for seemingly easy calculations. Let's say we're adding .2 and .4. Now what we get as a result is actually this, which makes little sense, right? This should be 0.6. And indeed, if you would compare the result of that with 0.6, you would get false. Why is 0.2 plus 0.4 not equal to 0.6 in JavaScript? I mean, that's certainly not what we learned in math. Well, it's all coming down to that binary system, which JavaScript and which actually all programming languages use behind the scenes, and the decimal system in which we, the programmer, work. When we say 0.2 and 0.4, we're of course working in the decimal system, so with a base of 10. Now JavaScript internally, as you learned, works with the binary system. And as I also just said, pretty much all programming languages do that. Now, therefore, JavaScript converts this number to the binary system for doing the calculation, and then basically converts it back to give us an output that makes sense to us humans, because we rather work with the decimal system than with the binary system, right? Now, that's exactly the issue. It's important to understand that in the end, numbers like this one here with decimal places are in the end just represented as fractions of integers, you could say. So for example, 0.2 in the decimal system could be represented by 1 divided by 5. And 0.4 could be 2 divided by 5, of course, in the decimal system. So in the decimal system, these calculations are super simple, right? We can perform them perfectly. Now, in the binary system, that's different. To understand this, let's first of all have a look at a calculation which we can't really solve, or where we have no perfect result in the decimal system as well. And that would be 1 divided by 3. In the decimal system, we get this number when we try to do that calculation. Because as you are aware, in the decimal system, we can't find a perfect solution for this division. And in the binary system, similar cases exist, not for 1 divided by 3 as necessarily, but for example for 1 divided by 5. Now for that, it can be convenient to find out how numbers are represented in the binary system. And that can easily be done by entering a number, for example 1, and if it's just an integer, you should wrap it between parentheses to tell JavaScript that now with a dot, you're accessing a method on the number and not adding a decimal place to it. So then you can enter toString here, and toString actually takes an optional argument where you can define the base to which you want to convert the number. If you enter 2 here, we're printing the number 1 in the binary system, which however still is 1, because in the binary system we have the numbers or the digits 0 and 1. So 1 is also 1 in the binary system. Now that changes if we try 5 here. Remember, 0.2 is the same as 1 divided by 5. Now 5 in the binary system is 101. So in the end, you're dividing 1 by 101 in the binary system when you're trying to express 0.2. You can actually see the exact result of that division if you execute 1 divided by 5 and then call toString at a base of 2. This number here, that's in the end what we end up with in the binary system if we try to divide 1 by 5 in the decimal system. So this is the result of the to the binary system converted calculation JavaScript performed. So this number, 0.2, in the end is this number here in the binary system, you could say. You can of course also see that if you call toString here and add 2 here as a base on 0.2. Here we don't need the parentheses because we already have 1 dot in there, and therefore it's clear to JavaScript that this is the number and this is then a method on the number. So this is how this number is represented in the binary system. And here it's simply getting cut off, but in the end this pattern here would be repeated infinitely in the binary system, just like the 3 is repeated infinitely in the decimal system if we divide 1 by 3. So there simply are certain fractions where there is no perfect solution in the binary system, just as there are certain divisions, like 1 divided by 3, where there is no perfect solution in the decimal system. And it's because of that why we end up with this strange result here. In the end, both 0.2 and 0.4 don't yield a perfect result. So if we then add these two not perfect results, we get an imperfect result, because we add two numbers which can't really be solved in the end. It's the same as if you would say 1 divided by 3 plus 1 divided by 3 plus 1 divided by 3. Now here we get 1 because JavaScript does some rounding for us to give us a result that makes sense, but in the end you are working here with 0.3333 plus 0.3333 plus 0.3333 in the decimal system. And hence, you would end up with something like this in a decimal system. You can't really reach 1. And it's the same for the binary system with 0.2 plus 0.4. You can't really reach 0.6 because in the binary system, both these numbers can't really be solved. There isn't a finite amount of decimal places that would be needed to represent each number. Now, often in JavaScript fixes this for us. It shows us a number that makes sense to us, even though in the binary system it can't really be represented. For example, if we just use 0.2, you just learned that there is no perfect representation of that in the binary system. Still, if JavaScript converts the binary representation, which, just to bring it back in memory, was this here, when it converts this back to a decimal number to output it to us, it converts it back into a perfect decimal number and not into something like this. But this is just a trick by JavaScript, and many programming languages do that. They, of course, don't want to show this to us. Instead, they want to give us a result that makes sense to us, and they're generally pretty smart about rounding the numbers they got in the binary system. Nonetheless, you can see that there is imprecision if you use another method, which is toFixed. toFixed does not convert this. Instead, here you can set a certain amount of digits you want to output. And for example, if you enter 20 here, you force JavaScript to represent this as a number with 20 decimal places. And you see, at some point of time, we can see that imprecision here. So JavaScript is really just doing some smart rounding for us when it just outputs 0.2. Behind the scenes, that number looks like that. Now, is that a problem? No, generally that's not a problem. For most calculations, this automatic rounding works just fine. Now, if you want to output a number to the user, you of course want to avoid that 0.2 plus 0.4 is printed like this somewhere on your page. To avoid this, you can use that toFixed method you just learned about. There, for example, you could force JavaScript to just display 2 decimal places, and you would end up with a perfectly fine number. And of course, you can specify any amount of decimal places you want. 2, 1, 0, whatever you want. And JavaScript will round it and avoid showing this imprecision here. So for outputting results to your end users, toFixed is a great way of working around that issue here. Now, there are certain other calculations, however, where you don't just worry about the thing or the result you show to the user, but about the result itself. Let's say you have an online shop and you're working with prices there. Now, if something costs 20.2 euros or dollars, and you send that to your server to charge the credit card by that amount, then behind the scenes, you are sending this number to your servers. And therefore here, in the end, you're charging not enough. Now, of course, chances are that when you're charging something like this, the payment service you're using automatically rounds this to fix your error or do anything like that. But chances are also that you in the end do introduce some small errors, and therefore you sometimes might charge too much or too little. And over time, even such small deviations can really end up. Imagine Amazon charging a little bit too much or a little bit too less on every transaction. Well, they're handling thousands of transactions every hour, of course. So that would quickly add up. And therefore, there are situations where you need perfect precision. Now, to get perfect precision, one common solution is to simply multiply your number with 100 in the end, so that you only work with integers. Now, you learned there are no integers in JavaScript. Everything is a floating point number. But of course, this integer here, whilst it not being an integer, would be this floating point number. And this can be represented perfectly in binary notation, so you won't have any imprecision here. So working with integers only can be one workaround around such imprecision here. You also can find certain JavaScript packages and libraries. By the way, libraries are a topic we'll have a closer look in detail later in the course, but certain third-party add-ons you can add to your page, to your application, so to say, which also provide you tools, utility functions to fix such imprecision. Or, of course, you are using some service, maybe on your server, or some third-party service your web app talks to, which fixes such issues for you. Again, often they may not matter, especially for outputting something to the user. You can just use toFixed, but in some cases where they do matter, you should be aware of that imprecision and that there are workarounds, like, for example, only working with integers by multiplying with 100, for example. So that was a lot about precision and numbers, but it's important to understand it. In modern versions of JavaScript, there actually also is an alternative to the normal number we worked with all the time, and that's a big integer. Now, the big integer type is a primitive value, and its goal is to allow you to represent numbers that are above the maximum safe integer we learned about, so a number bigger than that. If you, for example, wanted to represent a number bigger than that by adding an extra 9 at the end, you would see what I explained before. We get a totally different number because JavaScript only works with 64 bits and we would exceed that, and therefore JavaScript cuts the number at a certain point and shows a different number. Now, a big int can help us with that. You create a big int by simply adding an n after your number. And now you see, this looks a bit different here in the console because it's a different type. This keeps its precision, its value. And we can represent arbitrarily big numbers with that, because internally this is managed differently, not as a 64-bit floating point number, but instead in the end as a string. And JavaScript does all the heavy lifting of converting this around when you use it in calculations and so on. So the big int can be useful if you're working with very large numbers, of course not just positive ones, but also negative ones. Now be aware that there is no floating point calculation there, that there are no supported decimal places. You see I'm getting an error if I try to add a decimal place. It's called big int because it's only about integers, and it's the perfect type if you are working with very large integers. Of course, you can also represent smaller numbers with that. The question is if this makes a lot of sense. And then you can also perform typical calculations with it. Just important, you can't mix big int and other numbers. For example, 10n minus 4, where 10n is a big int, but 4 is a normal number, would yield an error. You see, cannot mix big int and other types. Use explicit conversions. So you would have to convert this to a big integer or this to a normal number before mixing it. You can convert it to a normal number with parseInt, for example. That would work. Or by converting 4 to a big integer by wrapping it with that big int function call here. Not new big int, but just big int like this. This is how you can convert numbers back and forth, and this is how you then can work with them and how you can run various calculations. Of course, conversion is only needed if you want to mix types. If you have a big integer and you want to multiply it with another big integer, you don't have to convert anything. You can just run this calculation like that. One important note, if you divide a big int, since decimal places can't be represented there, JavaScript will actually omit them. And we don't see it here because this can be divided with a perfect result without decimal places. But if we had 5n divided by 2n, then you see we're not getting 2.5n because this does not exist, as you see. Instead, we get 2n because JavaScript simply cuts off the decimal place that would otherwise be added. So that's the big integer. Not the type you'll use every day, but can be useful if you have very large numbers with which you need to work. Now that we learned a lot about numbers and big integer, before we move on to strings, let's have a look at the number and the math global object. We used some of the features of these objects already, and now I just want to have a second look and walk you through the important ones. Let's start with number. There we saw max safe integer, max value, min safe integer, and min value. You also have negative and positive infinity. These are special values in JavaScript, which you also can just type like this, by the way, infinity and minus infinity. And this is the value you, for example, get if you divide by 0. You'll not get an error, which you might expect. Instead, you get infinity because it basically approximates the result, you could say. So infinity is a special value you can get, and you can also check for infinity in places where you need true or false. For that, you got the isFinite method, also on the number object, but also available just on a global object, to which you can pass a number to find out if this is finite, like an example of 10 is true, or if it's infinite, as an example of, well, infinity, because that is not finite and therefore this returns false. So number is finite can be useful. We also have is not a number there. We saw that earlier already. Also exists as a global method. We got parse float and parse int here, which also exist globally though, and therefore we don't really need that here. And that's therefore basically it for the number object. More interesting than that is the math object. There you get various methods and constants or properties that help you with mathematical operations. You got the value for the e number, for pi if you need that in calculations, methods for calculating the square root, for working with a sinus, for example. Also the power of method we saw a second ago in this module already. The abs method to give you an absolute number based on some number you pass in as an input. And many more methods, like for example also the random method you already learned about, which also can often be very convenient. I can only recommend that you scroll through the various methods you got there. As you can see, there are a lot. Of course, the MDN docs are also a great place to learn all about them. And whenever you have a mathematical operation you need to perform in your code, chances are that you don't need to reinvent the wheel and you don't need to write your own logic, but that the math object has got you covered and provides the operation you want to perform. Before we move on to strings, here's a little demo with the math object and a little convenience function which you might actually need in many of your programs. We have math random to give us a random number. Now what does math random produce though? It produces a random number between 0 and 1. Now that's nice, but sometimes you need a random number between 10 and 20. What can you do in such a scenario? Well, we can write our own function that builds up on math random and allows us to provide an upper and lower boundary. Now for that, I'll create a new function, and of course you can create it in any way you want with a function declaration, function expression, arrow function, whatever you need, and I'll name it random int between. Now of course the name is totally up to you. Now here I expect two values, a minimum and a maximum value, so my lower and my upper boundary. And we want to return a number here. Now it all starts with math random, but of course that is between 0 and 1 as we learned, and that's not what we want here. Now to respect our minimum boundary, we can add the minimum. If we call this function, for example, with a value of 5 for min, we now get a random number plus our minimum. So we can't get a number lower than min because we add min. So we're already respecting our minimum, which sounds quite good. Now we also, of course, want to respect the max, however. Now to respect the max here, we need to multiply our random number here. What happens if we multiply it with our maximum? Let's say our minimum is 5, our maximum is 10. This gives us a random number between 0 and 1. We multiply this with 10. So if we have 0, which is of course very unlikely, then we would stick to 0, we add min, we have our minimum number. Sounds about right. If we have 1, then we multiply this by max. So if our max value was 10, now we have 10, and we add 5 to it. So now we would have a value of 15, which is above our maximum. So we actually need to multiply it with max minus min, so only with the range between max and min. Now if max is 10, and I can put this here to make that easier to keep in mind. So these are the values we're working with in our fictional example to verify the function. If min is 5 and max is 10, then this yields 5. If math random gives us 1, then this overall term produces 1 times 5 equals 5. We add 5 to that, we have 10, which is of course our maximum. So that is all right. Now theoretically that would be great. But even though it's not saying it here in the tooltip, but you could find it on MDN, for example, it's important to understand that for the random method here on the math object, 1 is actually not included. So the random number we'll get might be 0.999999, but we'll never get a 1. So as a result, the biggest number we can get here is max minus min. So that's 5. 5 times 0.99999, so that's almost 5, plus 5 is almost 10. Now, if we want to include both the minimum and the maximum here, so we want to make sure that both numbers can occur, then we're not finished yet, because right now this can never yield the maximum because random only yields 0.99999, and therefore we can only get close to the maximum. Now, to get the maximum, we can add 1 here to our multiplication term so that this actually is 6 for these values we're providing here. And therefore, the biggest number we can reach right now is 10.999999, right? Because we have 6 times almost 1, so we have almost 6 as a maximum result here, plus min, which is 5, we have almost 11. Now, of course, we want to stop at max, however, which is 10, and not at almost 11. And now we can leverage another function on the math object, and that's the floor function. Floor rounds this number down to the nearest integer. So we can wrap this entire term with math floor, and it will basically just cut the decimal places, you could say. So if we had this as a result, then floor will turn this into 10. And now we have a function which yields a number between min and max where both values are included. Now, of course, you can deviate that and you can play around with that. And if you Google for JavaScript, random between, and so on, you'll find many examples where min is not included, where max is not included, and so on. But this here is a pretty common scenario, which is why I wanted to show it to you. Well, and with that, if we give it a try and we console log random int between, let's say, 1 and 10, let's see what that gives us. If we save that and we go back to our page and reload, now we should get a couple of integers randomly, but never above 10 or below 1. So now we can run this as often as we want. We'll never get a number bigger than 10 or smaller than 1. Enough about numbers. Let's have a look at strings. Now, for one, I want to point your attention at something which you already know actually. Strings, of course, can be created in 3 different ways: double quotes, single quotes, and backticks. Backticks create a string with that template literal notation where you can dynamically inject dynamic values like this. And on any string, no matter how it was created, you also get a couple of properties and methods. For example, the length property to find out how many characters this string has. But then also many useful methods. For example, to uppercase, to transform a string to be all uppercase characters. Of course, the same exists for to lowercase. And various other methods for combining strings, for extracting substrings, for checking if a string, for example, starts with a certain sequence, like in this case, and so on. A great place to learn about all available methods is, of course, MDN. There, if you search for MDN string, you'll find this article. And on the left, you find all the methods on this prototype, which is in the end attached to each string you're creating. And there you can find out which methods exist and what you can do with them and how they are supported in different browsers. Now, this can be really useful to work with strings to remove excess whitespace, for example, with the trim method, to convert it to all uppercase, as you just saw, or to do many other interesting things with it. Now, that's strings, and that's the uninteresting part, because the more interesting part is actually what you can do with template literals. There, we only scratched the surface yet. We worked with template literals already. The idea here is that you could have some variable or some expression that produces a result that can be output in a string. And then you might have your template literal where you say, my name is, and instead of having to concatenate strings with a plus, which can be very cumbersome for long strings, you can use the $sign curly brace notation here to just inject any valid JavaScript expression. So any expression that yields a value which can be output as a string. Here I'm referring to the name constant, but we could also be calling a function, if we had a getName function here, that returns something we can output, or do whatever you want. Only important thing is, it has to be an expression. You can't put an if statement in there, for example. But that's what you already knew. That's the template literal syntax, and that can be really useful. Now, you can do even more with it than just output simple strings like this. You can create so-called tagged templates. A tagged template is in the end a function that works together with a template literal. It all starts by creating a function. For example, product description, and this will make more sense in a second. A regular function which expects, let's say, 3 arguments. And I'll come back to why 3 and what each argument holds in a second. Of course, you can name all these arguments or parameters however you want, but let's name the first one strings here. The second one product name, and the third one product price. Now in here, I'll just return this is a product. Nothing fancy, just a string. Now we can use that and, for example, create a constant product output, and there we add product description, but we don't call it like this. Instead, we do something which looks super strange at first. We add a template literal right after our function name. So there are no parentheses anywhere. We don't pass that as an argument to that function. We have our function name, and after that, 2 backticks. And that's a syntax we haven't seen before. Behind the scenes, JavaScript will call this function and kind of pass in this template literal, but not just like this as a single string, but it will actually split it up into, for example, 3 arguments here and send these into the function. Now, the amount of arguments it sends in actually depends on your template literal. So here we could have this product, and then, for example, in parentheses, which are part of the string, no special syntax. Then, for example, an injected expression here, where we have the product name, and for that, let's add a new constant here, prod name, JavaScript course, and refer to that here in our template literal interpolation syntax here, is, and then, for example, the price. So here, let's have the prod price and have 29.99 here. And then insert this here. So it's a regular template here in the end, if we ignore the function name in front of it, where we inject or interpolate 2 pieces of information into our otherwise normal string. The strange thing here is that we have that function name in front of it. Now, I said that JavaScript would call this function for us and pass this in, but not as a single argument, but actually as 3 arguments. Well, that will make more sense if we start outputting this. Let's console log product output here, product output, and see what this yields us, what this function actually does. If we save that and we reload, we see this is a product. So what we see here is actually what this function returns. So it looks like this function was called and the result of the function is stored in this constant. Okay, so let's see what happens inside of the function and what we actually receive as arguments here. For that, we can, of course, console log strings, console log the product name here, so our second argument, and console log the product price, our third argument. All of that gets logged here, and with that, let's save it and reload. And now we see something interesting. Now what we see here are these 3 outputs. These are from the lines 9, 10, and 11, which are just these 3 lines in the function. Now, for strings, we see we're getting an array. We're getting an array which consists of 3 elements, where each element is a string. And the interesting thing here is, in the end, these 3 elements make up all the text we have down there in this template literal, without our dynamic parts, so without the interpolated or the injected segments, you could say. This product, blank, opening parentheses, this is our first element. Then, between the first interpolated element and the second one, we have a closing parentheses, white space is white space. And that's exactly our second element here in this array. And then after our second interpolated value or segment here, we got a dot, which is also a regular string, and therefore our third element in this array is just that dot. So in the end, what this function does, or what JavaScript does with this special syntax here, is it calls this function here, product description, and the first argument of that function always is an array of string segments which are taken from your template literal and which represent the string parts between your dynamic segments. Now your dynamic segments, and of course here I should output this correctly now that I see it, your dynamic segments are passed in as additional arguments into that function in the order they appear in here in the template literal. So that's why if I reload again, we see JavaScript course and the price here. We see that here because these are our arguments 2 and 3 in this function, and JavaScript simply goes through your template literal, takes all non-dynamic parts and puts them into this first argument, which is an array, and then takes the dynamic parts and adds them in the right order as argument values to this function. Now, that hopefully makes sense. The obvious question is, why would we use that? Where can this be useful? Tagged templates can be useful if you have a scenario where you conveniently want to create some output. Could be a string, but could be something totally different as well, based on some string input. For example, you could be using that to take some input here, some input text, and convert this to a different text where you replace some values. For example, here we could check if product price is greater than 20, and if it is, then we set some variable, which I introduced in this function, price category maybe, to cheap here, and if the price is greater than 20, we set price category to fair. Now we could output our string down there by constructing a new template literal, for example, and then by injecting strings, the first segment of our strings here, which is the first segment of that template literal string here. Thereafter, the unchanged product name. Thereafter, the second segment of our strings, which is this segment. But then instead of the original price, we insert the price category here. And then we insert the last piece of our original string. So now we're outputting a fully dynamic string, a dynamically generated string, where we swap a value with some included logic. And especially if you, for example, have a more complex logic for encoding a numeric price into a category, as we're doing it here, then you might be better off using such a tagged template function here, instead of using a ternary expression down there, for example, which would take up a lot of space and could quickly be unreadable or hard to read at least. So that would be a scenario where such a tagged template can save you time and lead to a better, more readable output, because you can run your more complex logic in there and then just output the updated string down there in the end. So if we, for example, run this, we get this product is fair. We could, of course, also say fairly priced here, and they're pretty cheap regarding its price, something like that. And if we do that, you'll see here we got is fairly priced. So that's how you can work with that. And of course, there are many things you can do. You're also not forced to return a string here. Whilst that is a possibility, you could also return an object here with the name, which is product name, and the price, which is product price. And now you would have a function that simply converts a string into an object. It throws away the string parts you got and then just gives you the data that you dynamically injected there. If you needed that for whatever reason, you could do that and you would be getting an object without any errors, because you're not forced to return a string in a tagged template. Now, to conclude this module, let's have a look at regular expressions. Regular expressions help us work with strings. Consider this example. You're having an input, and there you get some user input, and that should be an email address, something like test@test.com. This is what you get from an input you might have on your page. Now, of course, users can enter anything in there, and by accident, they might enter something which is not a valid email address. Let's say for some reason the @ symbol was forgotten. Now, you want to verify whether what the user provided to you in your code when you work with that value, whether that is an email address or not. Now, a trivial test you can make or you can perform is you can use a string method for that, the includes method, and check if that string includes an @ symbol. And we would get false here, and hence you would know that the user input we got is not a valid email address. But a valid email address is not just determined by the existence of a @ symbol. Instead, we also want to have a domain ending at the end, .something. So, of course, we can also check whether it includes a dot, but that would also mean that something like test.t at test would be treated a valid email address because it includes a dot even though it's in the wrong place. And that's where regular expressions can help you. Regular expressions don't just exist in JavaScript, they exist in most programming languages, and they help you search for patterns in strings. Now, you create a regular expression in JavaScript in one of two ways. You can create it with the new regexp constructor, and then to this constructor you pass a string which describes the pattern you want to look for, and there is a rich regular expression language and syntax you can use here. Or you use a literal notation for creating that regex object, just like you can use square brackets to create an array object. You use 2 forward slashes like this, and then in between these slashes you define your pattern. And a simple email validation pattern could look something like this. The caret symbol here, then \s plus at \s plus, capital S, that's important in both places, \dot \s plus $sign. Now this looks super weird right now, but let's just accept it as it is and make sure you don't mistype. Now with that, you can use this, and as I said, it is an object, and call a method on this object. And there we could call the test method, and to the test method you can pass a string where you want to validate if it meets this pattern. And there we could pass in user input, and we would get false. On the other hand, if I test a valid email address, let's say here I test at test.com, I get true. Now, the reason for that is that this in the end describes a regular expression which says we accept any kind of word at the beginning. This symbol means we start from the left, so we have to start with any kind of word like test. Then somewhere in the overall string, I want to have the @ symbol. Thereafter, again, any kind of word, so this test here, for example. Then a dot, which we have here, and then again any kind of word with which we end this string. This is what this expression means in the end, and this string here, for example, fits into this pattern. Now, of course, there is a rich regular expression syntax you can learn, and it's almost like a programming language on itself. In the next lecture, I'll provide a brief introduction into this syntax, but by no means a complete overview of all the things you can do there. However, linked to the next lecture, you also find an external resource, a little bit of a more detailed introduction I prepared in the past, which you can have a look at, and also some MDN documentation to learn more. And I will also show you how you can find out which pattern is best for your use case. So let's learn a bit more about regular expressions. For that, I just reloaded this page here. And now again, let's create a new regular expression and store it in a regex constant. Again, you can create it with new regexp and pass the expression pattern as a string to the constructor, or use this literal notation with 2 forward backslashes. Now, a regular expression, as you learned, describes a pattern which you try to find in some text in a string. A simple pattern could be hello. So just a couple of characters, normal characters. This regular expression would yield true if we test any string which includes hello. So if we test just hello, we get true. We also get true if we say hi there, comma hello. or if we have hello anywhere in there. So if hello is part of the string, this yields true because we're just checking if this combination of characters is part of the string we're validating. Now we don't return true if I try to validate hello with a capital H, because regular expressions are case sensitive. So this here does not yield true because we're checking for hello like this, not for a lowercase or uppercase h. However, you could do that. You could also create this pattern in a more flexible way. You could say, well, I'm looking for hello, but I don't care whether we start with an uppercase or a lowercase h. You would express this by wrapping this into parentheses, then adding a pipe symbol, and then an uppercase h. And this means, well, we want to have a word which ends with lo and starts with either a lowercase or an uppercase h. And of course, we should store it in a new constant here to not reuse that name. And now if I use regex2, I can test hello, and you see we get true. Also, if it's somewhere in that string, but I also get true if hello starts with an uppercase h. We, by the way, don't get true if we just have lo. So the h really is needed. We just don't care about its casing. So this would be one example of how you can alter this to be a bit more complex than just a straightforward word. There also are other modifiers. You can also work with wildcards. So after reloading this page here again, I'll create a new regular expression. And let's say I want to check for lo, but I don't care about the first character. For that, you can use a dot here. And this signals, well, you want to end with lo, but you don't really care about the starting character of the word. So it has to be a 5-character word, but the starting character is not relevant to you. So then if I test hello here, I get true. If I, on the other hand, test just lo, I get false. On the other hand, I can use jello like this, and I would also get true. Or something like this. This all would yield true, but I have to have a starting character, and this is then a wildcard. By the way, you can also escape in regular expressions. You might remember our email regular expression. Email regex. There I used s plus, at, s plus, and then I used backslash dot in here. This is how we say, I'm not looking for any character, but really for the dot character. Since the dot in a regular expression has a special meaning, it's that wildcard you just learned about, you escape it with a backward slash, just as you can escape some characters in a normal string. Same, by the way, here with s plus. I escape this s here so that I don't mean the regular uppercase s character, but this now basically has a special meaning in regular expressions. It means any word, so to say. Now, there is way more you can do there. And as I mentioned in the last lecture, attached you find some links that allow you to dive deeper if you want to. I, however, also want to be very honest with you. Learning regular expressions and writing very complex expressions on your own will take some time to master, and you might not need it that often. Therefore, a lot of people, myself included if I'm honest, often look up certain patterns, especially if I'm not sure if the pattern I came up with is the best one. So for example, if you want to validate some email address in JavaScript, you can Google for email JS regex, something like this, or JavaScript regex email, anything like that. And you'll find some discussions on Stack Overflow typically, where you find some ideas. So here, for example, you find very complex patterns that match a lot of different email addresses, or you find the more simple pattern I showed you. Basically a combination of this one here and this one here. And this is, of course, not just possible for emails. If you want to validate a URL, so if you want to find out if a string holds a URL, you can Google for URL JS regex, and you would find this discussion with some ideas on how you can validate a URL. There you see a lot of different rules and syntax features of regular expressions in action. And again, with the attached resources, you can learn more about that. But if you just need to find a certain regular expression to validate a certain pattern, this is how you can find it and how you can work with it. It's also worth noting that you cannot just call test there. You also have a exec method on a regular expression. If you pass a string to that, and keep in mind stored in regex is this regular expression. So if you pass a string to this, let's say jello, which matches my regular expression, then you get back an array with some information about the pattern and where it matched in the string. You get the matching string back, but you also see where this pattern started in the string. And here, since the entire string matches my pattern, we start at index 0. If I would try to match this on, let's say, hi, jello, then you would see we got index 4 because the pattern we found in there, which was jello, that matched our regular expression pattern, that started at index 4. Index 0, index 1, index 2, index 3, and then index 4. So the fifth character was the first character of the matching pattern. So you also got exec if you need to find where in a string your pattern is matched. You also can do it the other way around. If you have hi jello here, then you can also call match on this and pass a regular expression to that. And you get basically the same output. As you see, matching pattern and where it started, but you call this on a string instead of on the regular expression. It's of course up to you which one you prefer. And that's it for now about regular expressions. Definitely an interesting and sometimes important topic. You got the basics here. Searching for patterns is a good idea and something you will do in practice a lot. And if you want to learn more, check out the attached resources, of course. And this is it for this module. We learned a lot about numbers and how JavaScript works with them internally, why we sometimes get strange results when working with floating point numbers and what we can do about that. We learned about the number and math object and had a look at how we can generate random numbers in a certain interval, for example. And now at the end, we had a look at strings and there specifically at template literals with the tagged template syntax here, where you have this strange combination of function and template literal to have a function which JavaScript calls for you with certain arguments, which then allows you to change your string, update it, run more complex logic to transform it, or return even something totally different than a string. Now, that might not be something you need every day, but occasionally it can be quite interesting to work with that, especially if you wanna transform a certain value. Let's say you do have a price, but you don't want to print the price but such a category. The more categories you have, the more cumbersome it can get to do this all with a ternary expression down there. And then such a tagged template like we have it here can be a great alternative.